Welcome back, and now we're going to do the second part of the previous video, which we were doing an IK dance. Again, this is a recreation or more simple version of this Unity project of someone who put together this really cool animated procedural dance. It's just kind of like a random dance of just moving end effectors around and then pushing all that data to Unity's IK system. So this way then it just moves the body based on where you basically just move little dots around. So in the previous video we moved the feet around and we moved the hip around and we got the Vegeta dancing a little bit. Now we're going to deal with the spine and we're going to deal with the hand movements. So let's get straight to the code because I'm trying to make this. The last one was kind of long, so let's try to make this one short. I'll try to clown around a little bit less. So one of the other things we're going to do, we're going to have a new class called noise cycle. Same thing with our number cycle, except this one just keeps moving forward through a Perlin noise. That's all it does, and it moves it based on a certain frequency per second. So if it does the same kind of functionality as normal number cycle, and like I said, it just keeps moving forward, and then it just has extra functions. Allows me to lerp. I don't remember what this one's for. I guess lerp two values by using the current noise value. So and it has a scale and it has an addition. So it lets us get our current frequency position. We can scale it and then we can add it and then we remap it to t, and then we get 1 minus t, and then we just use our regular lerp equation to lerp between the two values. So I guess I wanted to kind of just quickly lerp between values without actually having to do two function calls. So I just mix it all together because a lerp function is very easy to write. It's just that little tiny very small equation. So, and I have a get function that gives me a value what the current value is, and I'd have it asking for, do I get the whole value, which is the value between -1 and 1, or do I want it in remapped as 0 and 1? In certain instances I'd rather have the remapping because depending on what values I'm using. And again, it's using a scale value, so this way we can scale. So even though we're moving forward, we can still scale because if we're doing like noise on like a quaternion or position, I might want to keep the noise frequency in the same place, but to make sure that all three axes aren't moving exactly the same way, scaling it and adding to that frequency will give it some variations. So it varies, even though like I exist in a certain part of the Perlin noise value or the current frequency, I can kind of skip ahead. And no matter how I animate, I'm always going to scale the same amount. I'm always going to add the same amount. So this way, everything kind of stays together in a nice smooth loop. But it gives me the ability to kind of just move around a little bit. So this way, like I said, to add more variety. Because if the things don't look great unless you add a little bit of variety into it. So things are more random, or they look more random. So that's our noise cycle. So we have a noise cycle. So we just add that in. I say I want to move about 0.8 frequency per second. So that's how we're going to traverse through Perlin noise. We set up some more IK chains for our spine, for our left and our right arm. And now we're going to have a couple of settings. So we need to define how much rotation we want to do on certain things. So for the spine, I have a spine minimum and spine max. How much rotation do I want to apply to each bone in the spine? So for the x-axis, we're going to do between -8 degrees and 20 degrees. X-axis. So that means we're rotating this way. So it's just kind of like bobbing my head. Like I'm going to move back -8 degrees, but I'm going to move down 20 degrees. When it comes to the Y rotation, it's just 12 degrees left, 12 degrees right. So I'm defining how much movement my spine can do this. And then we have the Z axis, So again, it's between 13 and 13, no, negative 13 and 13. So it's kind of like this movement. So I'm just applying this rotation to the spine. So you do all three of them, you get like a wacky bobblehead type of effect. So that's but everything is nicely ordered. And we apply those ranges to Perlin noise. So this way, the Perlin noise is just going to move things all over the place. It's going to be a little wacky, but it's going to move. It's going to give that nice dancing flow. And then we kind of do the exact same thing for our arm movement. We defined how much to move around on the x-axis, how much to move on the y-axis, and the z-axis is a twist. So we're going to use that to kind of twist our elbow up and down. So this way we can kind of control it. So the elbow is going to go from here to down. So that's kind of our range of motion for our elbow, just out and down. Just 80 degrees is good enough. It doesn't have to be 90 degrees. It's just this. I didn't want the elbow to be like in the guy's in Vegeta's chest. So that's why I kind of stopped the twisting down to like 80 degrees. But these values can change. These are not like dead stone, but these values can change, and then that would actually change how the character moves. You're adding constraints. That's what we're doing here. We're constraining our movement to a set of ranges, and then we apply Perlin noise or a number cycle to it by using a gradient value, like something between -1 and 1, or a value between 0 and 1. And I don't remember what this value is, but we'll find it in the code, and I'll like, oh yeah, that's why. How much of the chain length to consider to minimum length? I think this is the controls. How much distance the fist moves away from the chest, or from the shoulder. So how far do I want to really move the end effectors? You got to remember, when you do an IK, our starting point is our shoulder, and then our end effector is where our hand's going to go. So I'm going to basically define the distance of how much movement to actually to do. So not only am I rotating in 3 different axes, I'm actually defining the distance the hand should be from the shoulder, essentially. So this way, so we can have the hand go out and in. So it's kind of this motion that we are defining. So now remember what that's for. So that's our range. It's a whole amount of 0.7 of the length. So if the chain is like 10 meters long, that means it's 0.7. So it's 7 meters of distance that we're going to consider the minimum. I don't know if it's the minimum that needs to. That's the minimum. That's how far you have to be. So it'll be from the minimum to the maximum length of the chain. I think that's how it works. And all the other settings stay the same. So we have our apply function. I comment out things so we don't have to. So we can just focus on certain parts. So we got the hip. So we're gonna still keep world transform, and we're gonna pass the world transform to spine. So we're going to apply the spine values. So right now we're going to some simple variables, and we're going to basically just do an Euler to Quaternion translation. So because it's nice and simple, it's like if we're rotating by X, Y, and Z, just those are the values. Just plop them right in, and it becomes a simple Quaternion, and call it a day. So right now we're just going to experiment with X. So we're going to use the noise clock, which an updated. So this way for every update we move it forward. And we're going to use the lerp function. So this way, I wanted to write the code really small. So this way I put in the minimum, I put in the maximum, and I wanted to say I want to scale it by 1. That means I want to keep the Perlin noise where it is, and I'm not going to add anything to it. All the other ones I'm scaling at 1, but I just move it forward. So there's a slight variation of how to scale the min and maximum values of each axis. Oh man, I'm trying to record 2 videos in one night. My throat's starting to go. All right, so yeah, that's like I said, we just get a range of that rotation, and then once we have that Euler or that Quaternion value, we grab the bind transform. So the the default position or the default rotation of the spine. So we're going to take the default position, the default rotation of the spine. We're going to multiply that by our rotation that we want to apply to it. And then we just update the bone, and we're actually updating our world position. Because instead of recalculating the world position when we deal with hands, because I need to know what the chest is, I'm using the spine to actually recalculate the world position as it goes up. So this way, when it's time to do the IK for the arms, I don't need to recalculate the position of the chest, because I already did it while I was applying all this Perlin noise to the spine. So again, this is me optimizing it a little bit. So this way, like I said, why not? Just if I'm going through and figuring out all the world rotations for the spine, why not just keep adding? And actually, I'm not actually doing world positions. Everything here is actually at local space. So I'm like the bind position is local space. So I'm just actually rotating the local space value and then putting it right back in. So there's no conversion of world space and local space here. So when it comes to the spine, I made it nice and simple and just keep everything in local space. So once I have everything in local space, I can just keep adding it to my transform, and just because like when you add to the transform, you just add the local space of the child to the parent's world space, and then that becomes the child's world space. And again, that's so I can just accumulate the world space up to the chest. All right, so let's look at what it looks like. And there you go. And this is what Perlin noise looks like when you just apply it to the x-axis of rotation. So you just bobbing back and forth kind of randomly. Sometimes a little slower, sometimes a little fast. It all depends. And it's nice and slow. Now it's starting. Yeah, now it's nice. So Perlin noise gives us this random but smooth movement. Now we can just apply all three axes. Refresh, and there you go. Now the spine's not really moving. There you go. And that's how we apply to, and this is how we did with blah, 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 blah. And this is how we handle the spine. It's just some ranges, and then just apply it through the chain, just through an array. I think this one's supposed to show me the current position of the chest. So this is where the chest is, because this is based on the actual movement of the feet. So that's where the chest is pointing if it actually, the skeleton was moving along with everything else. All right, for the next part, I need to freeze frame things. So that means I have to stop the animation and do a single movement. Refresh. So there you go. So that's freeze frame. All right. So now we're done with the spine. Now we have to contend with moving the arms. So let's just move one arm. So we're just going to apply arm. We're going to go check out the arm function. So we just pass in our chain, we pass in the world position, and this is the position of our chest. Now, one thing to keep in mind is that when we do, like I said, when we deal with IK, we get the start of the chain, and then we get the end effector, and that creates our IK target. To get the world position, I don't want to recalculate everything. So sometimes there is a bone, I think it's called like a shoulder bone or a clavicle. I can't say it's that little bone in your kind of like in your chest, clavicle bone. Well, there's usually a bone like this here. There's a bone between the chest and the start of your shoulder. So I'm in my little code. I even put a warning that I'm doing a little hack where I know there's an extra bone. There could be more than one bone, or it could be no bones at all. So if you wanted to write a dynamic dance that can work with any skeletons, you kind of have to check to see how many bones are between the start of your IK chain and the chest. So this way, then you can then easily calculate the world position of your starting chain. And since I know there's only one bone because I'm using this as a test, I'm just going to end up just calculating one. So I do have a big warning. So I don't want, if you guys are putting another mesh in here and there's missing bones or extra bones, things might not work well because you're not calculating the positions of the start of the shoulder. So just keep that in mind. Every skeleton is different. Most tend to have that extra bone between the shoulder. Sometimes I've seen there's two bones. I don't know why. In some like really low poly versions, don't have any bone at all. So chest, the shoulder bone or the upper arm bone is disconnected, and it's just positioned completely in the air. All right. Let's see, where are we? Let's see what this gives us. All right. Why is this in a bad position? I know it. Let me apply everything. Because everything wants to move, but I'm freeze framing it, and things don't line up correctly. I want you to be able to see it. So it's a freeze frame, so it's no big deal. There you go. So, all right, where are we? So, okay, we're going to deal with the arm. So, we pass in the world position. Let's see, we add the shoulder. So we get the parent of the chain, so that's going to be the shoulder bone or the clavicle, whatever bone. And then we can get the shoulder. So now we know what the chain world position is. What else? We're going to take that world rotation and we're going to define 3 axes. And we're going to know if we're mirrored or not. So this way we can use the same function for the left arm for the right arm. So by having this little flag that says mirror or not. So you'll see certain parts where M is going to be applied. And so it just mirrors the x-axis. Mirrors the y and z based on the x-axis. Yes. Or yeah, something like that. All right. So, and that's what we're seeing. This is the shoulder position. So based on I think it's based on the, what is it based on? So it is world T. It's based on world T. So world T is actually our chest. So I'm defining the axis based on our chest and not where our shoulder is. So this way I want to create a movement. So the idea is that now we have an axis defined. And remember I said we need to move the arm. We need to rotate it. So this is our rotation. So we're going to rotate, from our X. We're going to rotate from our Y. And we're going to rotate from our Z, because that's forward. So that's forward. That's our forward. So that's going to be our twisting action. So we're going to twist our elbow from sideways to a downward motion. So those are 3. So now we know what our axis of rotation is. So here this time around, I'm doing something a little bit different. This time I'm actually going to I'm going to do this differently, because this is going to be like right here it says this can be done better by using Euler to Quaternion inversion, but I wanted to show you how you can piecemeal Quaternion rotations order, how to piecemeal Quaternion rotations. But order is very important. if you add these in the if you combine these rotations in the wrong order, the rotation would actually come out not how you expect it. So you always need to to do like the rotations you expect. You rotate by Y, X, and then Z, and then everything is cool. So we're gonna do. I had this here. I don't remember. So whatever. So the first thing is we're going to take our range for our arm, and if it's mirrored, I'm just going to flip the sign. That's all I'm doing. I'm just flipping the sign. So some range might be negative, some might be positive, and if I'm doing the other arm, then I want to flip it. So that's what's going on here, and I want to lerp it. And I want to lerp it on a noise value, and I want to take an add and an offset. Now this offset is so this way the left and right arm aren't in sync with each other. So that offset, so I'm like I did before, it's like I'm adding on to the Perlin noise frequency. This one is for one arm. I'm going to add probably like 0 offset, and then for the other arm I'm going to add maybe a couple of more values or an extra value. So this way the two arms are not in sync, so they're not doing the exact same motion. I want to keep them random, but I want to have one function. So that's why you have the mirror, and we have NF offset, so the noise offset. And I guess I can just apply the IK. Refresh, and there you go. If I refresh as much as I want, you'll see that this arm, this black line, will always rotate around, and this blue line I think is the elbow. So let's just do, I don't know which one. I didn't comment to say which one is which. So that's the end effector. So yeah, so like I said, we're just defining that angle rotation. We're gonna say we create a quaternion that rotates on the y-axis at that angle, and we just multiply to rot. And rot, what does rot start off with? And rot is just technically I don't have to multiply. I could probably actually just copy. That probably makes more sense to copy, because I'll probably get the exact same result. But to start this, because copy would actually be less memory, less CPU intensive than actually multiplying two quaternions together. So technically, I should really just copy. But to keep, oh, I closed. Did I? Oh no. So yeah, if I do copy, there would be no issue really. Yeah. So it's the starting rotation. So let's leave it there, because that's actually correct. I guess I just copy and pasted and made sure everything's equal. But as a starting point, that's just our starting point. And then we just do the exact same thing. We get the range for our other axes of movement. Each one has their own different offset. And we create a quaternion, and then we multiply a rotation. So we're just accumulating the rotation. So over here, first we create our Y rotation. Over here, we create our X rotation, and then we multiply that to our Y rotation. Then over here, we create our Z rotation, and then we multiply that by our YX. YX rotation. And now we finally have a YXZ rotation in quaternion form. And again, all this is a lot of multiplication in quaternions. So ideally, you're better off doing this. Like, this is the easier version. This is the simpler version. But again, like, if you want to optimize it, this is the way to go. But if you want to be purely quaternion based for some reason, this is how you can go about it in a different way. But like I said, this is less efficient and less optimized. All right. So now we have basically this rotation. Now we just apply it to our world space rotation from our chest. Let's see. So the idea is, so based on all these three axes, we're basically in this range essentially between blue, red, and we're basically trying to move the arm in anything around there on the axis. It's getting late and my throat's starting to bother me. All right. So we add our chest rotation. So now we kind of have this world space rotation going on. All right, so we take that rotation, we calculate our z-axis. So z is going to be the direction of where our end effector is going to go. So essentially, like this green line is z, or where z is. So we're applying that new rotation. And that new rotation from a straight line takes us straight this black line. So this is the Perlin noise position that we end up calculating in world space. So we're basically taking that forward direction and moving it to this. So this is the Perlin noise position or rotation. And then we do the same thing for the x-axis. This allows me to rotate it. So that allows me to, so if green is now over here, then let's see. I think this is blue. Or is, oh, I think it's this one. And that's our X, and that's where we want the elbow to be. All right. I'm like zoning out now. I'm sorry. So, okay, yeah. So, like I said, the Z, by rotating it, because like I said, we already have predefined the world position. Now we're going to rotate it, and now we know where the end effector, like the direction toward the end effector. This one helps us determine what our rotation is, so we can actually rotate it our elbow. So that's our x-axis. Now we're going to figure out the length of the end effector. So we use our noise, and we take the chain, multiply it by our minimum scale. So that becomes our minimum value, and chain becomes our maximum length, and then we just get a Perlin noise alert between it too. So once we have that length, we then multiply the z-axis by length, and that's why the black line doesn't go as far as the green line does, because we're adding Perlin noise to the actual length of our chain. So that's why. So from the shoulder to the hand, that becomes a motion that's driven by Perlin noise. And yeah, then we apply the IK. So we give our IK, we give our world position. This defines the end effector, and our x-axis is the up direction that basically the direction that we want the elbow to be pointing at. So we're defining it like it's going to be the up direction for IK target. Those are from previous videos. So that's basically the direction we want the elbow to be pointing at. And that's it. And as many times as I refresh it, the hand is going to be a different place and different lengths. So let me get rid of all this jazz. And then just apply the arms. Refresh. Oh, they're mirrored. Why are they mirrored? Oh, did I forget to... I think I forgot to add the offset. So that's why I said I have that offset value, because I don't want these guys to be mirrored with each other. Say they're mirrored, I don't want them moving the exact same way. So by applying that offset, let's try 1.2. Sometimes like a really odd number. Usually a good... There you go. So, refresh. Yeah, it's good. That seems like all the arms are going in a different smooth direction. All right, that looks good. That looks like a good offset for the two arms. And I should be able now to now move the animation forward and do refresh. And there you go. We have a dancing skeleton. Let me get rid of those debug lines. We don't need these anymore. How long is this video? Oh, it's 30 minutes. We're done though. That's it. It was like I said, we just had to move those things around, just rotate it, blah blah blah. And there you go. Look at that. And like I said, it was just defining constraints of how we move it from the axis of our chest. And if I would bring Mr. Vegeta back, save, refresh, and there you go. And we don't need this. Let's refresh it. A nice full screen. It's not as cool as this one. Like I said, there's more purling noise and there's more movement, and it's at a faster tempo. And he uses, I think, different constraint values. So like I said, if you like over here, this one shows you that he's playing with the different ranges. It changes how the dance moves. So again, like this is the basic idea of how he put it together, and this is all the movements, how to do it. And it hopefully give you some good ideas of how to actually do procedural animation. You don't have to magically move all these bones around. It's not magic. It's like now that we have a nice IK system, all you have to do is just randomly move lines, like points around, like I had the dots for the end effectors. And just say, okay, well, now I know where the end effector is. I just need to know where the start of the chain is, and just do an IK. And all you have to do is just move points around. And sometimes you have to anchor them. Like for the arm, I have to anchor it to the shoulder. So, but then I need the axis of the chest. So I use the chest as the axis of rotation, and then I can use that to figure out the direction of where I want my end effector to be, essentially. But at the origin point of the shoulder, or you can use any point really. You can use a point of the face or whatever. But it makes more sense to move the hand, even though I use the direction of the chest, because the chest and the shoulder are almost identical. You can move the chest a little, the shoulder a little bit, in its own different, so it's not completely like the same axis direction as your chest. But we're not dealing with that, so we're just make things nice and simple. So you can use. So this way you know where forward is. So you can always know where forward is. And that was the whole reason why I did that. So this way you can always know to move your hand forward, then move it out, move it forward, move it up, down, and then you can rotate. And then, of course, then you got that. So that's really why I don't remember if he did it the exact same way, but it's the same idea. And you saw how the feet worked. We moved the end effector, we kept the feet together, and then we rotate it based on the look direction of the 2 feet by using a cross product. So there you go. This is a random dance. I don't know if there's I can probably speed it up if I were to change some settings. Let's see. Let's see if I make this a 9 for our step. So that should make our... Yeah, that's too fast. What was it before? Let's try a 7, like nice in the middle. A little faster. There you go. He's grooving. And then we could do the Perlin noise too. I could make it move a little more. How about have we do a nice big... Oh, too much. Too crazy. The Perlin noise one, probably not so much. If I use a smaller value, you traverse through Perlin noise. So his hands are going to be a lot more smoother or a little slower in motion. What was it? Let's try 6. There you go. That's not bad. You know, the feet are a little bit faster. The hands are a little slower. You know, maybe 1.1. Move the hands a little faster. There you go. Now it'd be nice if we add a little bit more randomness to it, like to the hip movement, a little bit more randomness to the rotation. So you're rotating back and forth at different angles. Maybe sometimes you do 90-degree rotations, and another time you do maybe 50 degrees or 160, whatever. So you can now that you saw how noise is done with the hands, you can do that with the hips, and you can do that with the feet too. The only thing we're also missing, that probably why it doesn't make it look as good as the other one, because we didn't do anything to the face. And the head is the same idea as the arms. You get the position of your face, get the forward direction, or actually, you know what? Use the chest as the axis of direction, and just recalculate a whole new rotation. Just define some ranges, how much you want to move up, how much you want your head to move, how much you want your head to twist, and then apply that to the head. And the head, just do it. So what we did for the spine, you can redo for the head, and then now you have the head moving in a random spot. And yeah, and there you go. And the other little bits and pieces that are missing is like foot IK. So this way the feet fixes itself. So this way it's nice and straight on the floor. But those are like little bits and details that the system doesn't handle yet. That hopefully we'll do in the future. But overall, there you go. We have a procedurally animated dance. It's perfectly IK, and it's good. Like I said, there's room for improvement, but the basic idea is here. It's a nice starting point. It gives you things to think about when you want to experiment. Now you see how you apply random and noise to rotations and things like that. All right, so this one's almost 40 minutes. Let me just cut off. My throat's really starting to kill me. Hope you had fun. This was fun. This is my second milestone for the IK system. The first one was to figure out all those main IK solvers for the IK rigs to duplicate what Ubisoft did. And now the second milestone was to actually get the IK system to the point where we can actually animate with it really well, and have an API that's not too unruly. There's always still more room to improve the API a little bit, but overall it's not that hard to use anymore, which is pretty easy to do. That's important, because if it's easy to do, then it makes it easier to experiment more, like things like this. So that's the end of the milestone number 2. Milestone number 3 for the IK system is to start doing bringing in animations like walking cycles, running, fighting, and do a lot of animation additives. So this way, you might have a certain walk cycle, and then you can apply additives to it. So this way you can actually change it and apply, and you can do animation and IK together. So you can have a walk cycle, and he's walking up a hill, or he steps on something, and the foot, even though it's being animated, will actually raise up and down because it's touching something. So that's where we can apply like animations with IK, and we can do additives on top of that. So that's going to be part of the next milestone for the IK system. So this way we can start walking and running, maybe climbing and things like that. So that's the next big milestone of our IK system. Because I want to make a small little simple arena fighter using Goblin Slayer. So we're working toward that. That's going to be the end of all the IK and animation stuff when we reach that point where we can actually control a character and have it fight other characters on screen. Simple hack and slash button mashing type of stuff. But yeah, so that's gonna take a long time. That thing took about 6 months to get to this second milestone. It took 4 or 5 months to get to the first milestone. So it's pretty much a whole year officially since I started doing the IK system. So it's been a year. Pretty much a long time to get to this point. Hopefully it might take another year or two before we get to, I just need more time, but we're getting there. Moving forward, I'm going to do 3 or 4 videos related to springs, so we can do springs with position, rotation. We're going to do jiggy bone because that's also related to springs, and keep saying ums a lot. And I'll probably finish it off with maybe experimenting a little bit with soft. What's it called? I forget what that was called. Not skin. Soft body. Soft physics. Soft body physics. I think that might be it. I think that's what's called soft body. Where like you have like the mesh move around more like skin would be like. All right, let's just say it. Like if you're going to touch a boob, how it kind of flexes back into shape, or things like that. A lot of the soft body stuff I've seen is related to how a boob jiggles and moves, and how if you were to press if your finger into it, how it springs back into position. So it's soft body physics. I think that's what's called soft body physics, and that's all related to springs. So we're going to escalate. So we're going to go from position, rotation to jiggy bone to IK chains, and then probably a little bit of soft body physics. And like I said, it's all the same. Once we get all the equations down and figure how all of it works, then we can probably build that nice big thing at the end. And the spring physics stuff, we're also going to be building a nice little project, maybe another little mini game for not Minecraft, Fortnite Baller, which the springs would actually work really well with some how to animate it. So yeah, that's it. I'm done. Hope you enjoyed it. Hope you learned a lot with the IK. We're gonna leave IK away for a while, do some springs, but we're gonna come back and do bones with springs. So with this, we can have a wagging tail, we can have hair, maybe control some clothing like skirts and stuff, because all that is related to IK chain, not IK chains, just regular bone chains, and then applying spring physics to it. So a lot of that'll probably be the 3rd or 4th video in the series, mini series. So now I'm doing a little mini series. Yeah, it's gonna be fun. The next couple of videos are gonna be fun. We're gonna really explore. So this week we're gonna start controlling hair and clothing a little bit on our 3D models. So when the characters are moving, maybe we can apply some things to Vegeta's hair, and his hair can be waving around, while he's moving around. So we could, we'll have some things. And I have another model of another character that I can probably use for jiggy bones and seeing how the hair moves when the character moves. So I guess I'll end it here, and like I said, hope you had fun. If you have $1 to spare, please go to my Patreon and just donate $1. That's all I really need. A nice little tip be great. If not, who cares? Source code is available for free, and who cares? As long as you're learning and you're having fun, right? I'll see you guys in the next video.